So we know that reducing congestion is hugely important for modern cities. Researchers and practitioners have developed various kinds of traffic control systems using advanced technologies, big data, and artificial intelligence. But we can still see these kinds of severe congestions happen from time to time, especially following disruptions such as extreme weather, special events. The question we're trying to ask is, how can we improve the traffic throughput even when congestion already occurs? To answer this question, we need to look at the relation between traffic flow and density, which is referred to as the well-known fundamental diagram. As you can see in the figure, the traffic flow goes up as the density increases to the critical density. After that, the traffic flow drops as the density increases. So in theory, the fundamental diagram is well defined both before and after the critical density. But using real data, it was found that the diagram can be much more scattered after the critical density than it is before the critical density. To accurately characterize this relation after the critical density, researchers have proposed various classes of models of different levels of granularity, such as the cellular automata kinetic wave model. However, the majority of this model lead to well-defined formulation for congested traffic, but the resulting fundamental diagram vary greatly. Not only that, there can even be hysteresis loops in the fundamental diagram, which, by the way, was observed several decades ago. Hysteresis loops in the fundamental diagram mean that the traffic follows different paths during acceleration and deceleration. So there can be clockwise hysteresis loop and counterclockwise hysteresis loop. Even the highly scattered fundamental diagrams for congested traffic, our overarching goal is to develop new models in order to reduce congestions. However, that is the grand challenge for traffic engineering. So currently we are working on an important first step toward this goal, which is to capture the evolution of congested freeway traffic at road segments. So why freeway traffic? The reason is that freeway traffic networks are less redundant when compared to urban street networks. So slight congestions cannot propagate evenly, and then this can lead to more severe congestions. We first identified the metastability using the physics-informed data-driven approach. It is data-driven because no traffic flow model is involved. The idea of this approach is that we model the road traffic as a dynamical system with stochastic state transition. Now suppose we have measurements about the state of this system, which can be traffic flow and density. And also we have the equation that connects the dynamical state and its state transition driving force, aka the potential. Then with a little bit of mathematical manipulation, we can solve for the driving force and the PDF of the stable states. And then using the PDF, we can then obtain the solution to the stable states. In the example of the tropical forest system on the right, we have the measurements about the tree cover and precipitation, which can be considered as the perturbations in this example. Then using this data-driven approach, we can obtain the function of the state given the perturbations, which is represented by the solid and dashed lines on the bottom and the potential function f in the upper half of the figure. The data we collected are the sensor data of the Twin Cities highway in Minnesota. We have the measurements of the traffic flow and density at about 1,300 sensor stations for 6 months in 2016. And using the data-driven approach, we found that metastability does exist in congested freeway traffic. In the figures obtained using 6 months data, we can see that for the chosen stations, there are two branches of the stable states for congested traffic. However, density intervals with two stable states are different for different sensor stations. To make sure the observation is not impacted by the amount of data we have, we also look at the results using 4 months. We can see the figures. There still exist two branches for congested traffic at those stations. And moreover, using only 2 months data, we still have similar observations. But we do know that this phenomenon only occurs at a few road segments. The reason might be that the traffic at the Twin Cities Highway at many road segments are not very congested all year round. So the traffic will mostly follow the high congested state without transitioning to the low congested state. We next use the model-driven approach to validate our observation. The intelligent driver model is adopted here to simulate the traffic on a ring road. This model is a car following model for the dynamics of a vehicle considering the impact of its preceding neighbor. If you are familiar with IDM, you may wonder why this basic model, which was proposed 20 years ago, when there are more advanced variants of this model. The reason is that we choose this basic IDM to make sure that metastability is not a result of the modifications to the basic IDM. So we ran parametric analysis using this model. First, we look at the desired speed. We can see that for large value, there exist two branches in the fundamental diagram. And for the desired time gap, we can see that there are also two branches for large values, but there are no metastable states at low values. Moving on to the different jam distances, we can see that again there are two branches for large values, but there are no metastable states at low values. In the future, we will derive the function for the metastability first, which will allow us to evaluate the impact of disturbances on the function and also predict the critical point before undesirable regime shift from the high congested state to the low congested state. Also, we will scale up the metastability to the from the road segment to the network-wide congested traffic. This scale up refers to the clustering road segments using metastability and then aggregate them depending on whether or not metastability occurs at that road segment. Then we can apply boundary control strategies to improve the traffic management.